Better.
All right, good afternoon, everyone. Everyone have a seat, please. So today we're going to do another review session. So last time we did the cross-flow heat exchanger, and what else? The time before that?
Sherman too.
Exactly. So then what's left? Perfect. So we will do double part today. So here's the problem. It's actually from chapter 8, problem 31. And this is actually taken from the alternate problems. Basically, it's part B and part C we're looking at. Please have a seat. So the problem here is basically a earth double heat pump that we're going to look at. And again, just like for the previous ones, we will go through the same process of steps of finding the properties and then trying to evaluate for different, basically for different properties. So obviously, for properties, obviously for different flow rates, different heat transfer rates, and all that stuff. So in this problem specifically, we're looking at a double pipe heat exchanger. It's very similar to the project that that Team Silverado worked on, right, or are working on. The same figure. It's from page 595. You look in there. And for that double pipe heat exchanger, we're actually assuming it involves water and R22. All right, and that's the refrigerant 22. And also, in the problem itself, it tells you the assumed steady-state operation. Right? And on top of that, we've also given the saturated R22 flow, which is at 0.1 kilogram per second, and it's at 5 degrees Celsius. Do you guys remember how it goes? You have the book, which should tell you. So once entering, what is the saturation? Is it saturated liquid or saturated vapor? Liquid? Okay. It's exiting as?
Saturated vapor.
Alright, that's good. And how will you find the information? And there was a question actually. For that, I actually looked it up. I looked up one of the websites. So actually click on this link, and we will do exactly that. And this reference is actually posted on Blackboard as well. So you can actually look that up on Blackboard. It's under the alternate problems references. If you want to look up that. But nonetheless, I'll also try to post this presentation as well for your reference. So nonetheless, go ahead and click this link. You can get the properties from there. Also, they also give you the information in terms of the heat of vaporization, and also they give you in terms of the water information as well. And for the water information, again, you can go over your book, your textbook, and we will go over those two properties there. So, I think it's the University of Wisconsin. They actually developed this software that we can use, and you can actually compare it or actually look up different properties for given different conditions. And in this case, we want to choose the fluid. In this case, is going to be R22, and then you can enter two conditions here. And typically, the conditions can be the options. You can pick temperature, absolute pressure. You can take density, quality, and internal energy, and enthalpy and entropy. It's any one of those. Right. So in this case, for R22, what do we know? No, you're giving the heat of vaporization. There's no enthalpy for R22. What is what's given to you in that problem? They call it enthalpy. Yeah, but it's not the same thing as enthalpy of a certain state. So the vaporization is from. What does vaporization mean? It's going from one state to another state, right?
Yep.
That's the same enthalpy that they're talking about here.
Yep. Quality
specific state.
and temperature.
Perfect. Quality and temperature. What's the temperature?
5 degrees Celsius.
Alright, so if you want to pick degrees Celsius, you have to change the international units, which I'll do that right here. And you put 5 degrees Celsius and do the quality. So what's coming in? Quality coming in?
Liquid.
So it'd be quality is what?
Liquid. 0.
Perfect, 0. So quality of 0 means it's liquid. Quality of 1 means? So you plug that in, and then you calculate, and then give you all the information that you need to know. The temperature, the thermal expansion, the viscosity, thermal conductivity, Prandtl number. These are all estimated values. Okay? And so from here you can get the density information. You can also get the heat capacity, the Prandtl number, and thermal conductivity. Because these are stuff that you need, and viscosity that you need from the for solving your solution. So again, if you go back to chapter 8, I think it's section 8.3 or 8.2, they actually give you the steps. So for that, you can notice read the properties for that. So nonetheless, you can use the software and you utilize that to your advantage. And then the last thing that you need to know about the heat exchanger. We talked about the fluids in the heat exchanger. So the important part of the heat exchanger, especially from a mechanical engineering perspective, is how to build it. And in this case, they always tell you that they're building it as copper tubings. Right? Two copper tubings. One is inside, one is outside. One is a 4-type M copper tubing, the other is 3-type. And again, you can find this information in the textbook. It's given to you. And then you're giving a length of 2 meters. Okay, that's also in the textbook. And we are told to find, so in this case, and specifically for the problem that I assigned, I asked you to find the overall heat transfer coefficient and also the property pressure drop for the water and the R22 streams. Okay. So again, this is an example problem.
What was it? Find what was the second thing? Pressure drops.
Pressure drops, yeah, the 2 pressure drops.
And what was the third thing you had?
The 2 pressure drops. The last 2 items. All right. So for the solution, again, we can use MATLAB. Unfortunately, for the virtual desktop, I don't have the engineering lab working right now, so I'll just go over the code that I written up and post it to you, and then and obviously you can do it on your own and figure out what's best or how you can solve it on your own. But nonetheless, this is just to give an idea of what it looks like doing it in MATLAB. Obviously, last time, hopefully you can say better this time because it's actually larger, right?
Yeah.
So you can say it better. But if you notice here, first thing I wrote is % A fluid properties. The reason I put %, it actually makes you a section in MATLAB. So if we just put 1%, it just comments it out. But if we do double %, it makes actually a section. So you can actually make different sections. So the 2% to me, this section is about fluid properties. And this section involves, obviously, as you can see here, first thing I put is R22 refrigerant saturated. And I got the information again from the website that was provided to me. And it was what I found out is the pressure to be about 0.585 megapascals at that 5 degrees Celsius. Okay? And we said inlet temperature is 5 degrees Celsius and outlet is 5.1. Again, it's not really actually 5.1, but what do we say? Why do we add the extra 0.1 again? Yeah, that's true. It's irreversible. And also more important in terms of calculations, if you do
don't get a 0.
5 minutes, I get a 0. Exactly. That's the main reason. But that's true also. That's very important to note. There's also irreversible involved as well. So that also kind of accounts for that. And then again, the reason that the temperature shouldn't change is because you're just going from one phase to another phase, and it's saturated. And for the density, if you notice, you see the 1260 over here, right? And then remember one approach that I told you to do is take the average. I took the average of the inlet and the outlet temperatures. So this is what I did. I took the average of 1260 plus 24.8, which are the density of the liquid, saturated liquid, and saturated vapor. So that's one approach. Again, you can do many different approaches, but this is one approach you can take to solve this problem. Okay. And also, so that's the information that was given. And also, I put the mass flow rate for it as well, the heat capacity for that as well. And I think that should be an average, but nonetheless, I think that's still a number you can use. The viscosity, also did an average of that, and also thermal conductivity. So I kind of number all that, I took the average of those. And obviously the most important one, the 200 kilojoules per kilogram, the heat of vaporization or the enthalpy of vaporization, I also noted it here as well. It's part of the properties. Okay. And again, I put it as latent heat for the hot fluid. Okay, and why do we, yes?
So for each of the properties, we take the fluid, the liquid and the vapor, and just...
And you can take average. So
average.
It's kind of like you guys did the average for the temperatures, right? So obviously you don't have a temperature difference here. What's the difference here? It's a liquid state and a vapor state. So that's, again, it's not the best approximation. But nonetheless, it can give you a reasonable estimation so you can actually go forward with the calculation. But most of your, in terms of your heat transfer, all of your heat transfer is coming from the vaporization. Basically, none is coming from the change in temperature. Okay, just remember that. So that means, then we move on to the next part. So again, we're still in fluid properties, and we look at water. So in this guy, I estimated, at temperature of 10 degrees Celsius. You can pick whatever you want. That's reasonable, right? So I estimate to be 10, but it could be 15, 16, depending on what it may be. But I estimate to be, so typically you want the temperature difference to be about 10-ish, right? So that's a good estimation. And then you can take the average of that, and based on that, you can look up in your table, and then get the densities and the mass flow rates and etc. like that. And if you notice, I didn't do much of the averaging here because liquid water, in terms of liquid water, what do we know about it in terms of its properties? It's incompressible, so as a result, a lot of the properties stay relatively constant. Okay? And again, all this information should be in your textbook. I forgot which table it is. You can look it up.
620, page 620.
Page 620?
I think so.
All right, so page 620, you can look it up and get the information. It's in the appendix. And you can double check information. All right, so we're done with fluid properties, right? So if you go step by step, you've done the fluid properties already. You already established steady state. You already established the temperature we're using. You're using an average, right? And based on that, we found the properties. Now we have to move on to the actual design of the heat exchanger. For that case, we're using the tubes, which in this case are M-type or M copper tubings of 3 different sizes. And all you have to do for that is look up on your appendix, I think it's table D.2 or something like that.
Yeah,
exactly, and then you look that up, and then obviously everything's in centimeters, so I convert everything to meters. Right? And then, and as you notice, these two are your pipe or your tubing, inner tubing, and then the IDA means annulus, right, or basically the outer tubing. So there's space between the outer tubing and the inner tubing. Right? And if you notice, we don't care about the outer diameter of the outer tubing. Why is that? What's one of our assumptions that we make?
Nothing's lost.
Exactly, it's 80 back. Good. And then we set the length to be, I don't know what, 1/2 here should be 2, right?
They have 0.5 meters.
In the
0.5.
Okay. So I actually posted what in the first. So you ignore the first slide, just go by the books. In this case, this is correct.
This is half a meter?
Half, yeah.
0.5.
He's correct that. Yeah. I thought for some reason I was thinking 2, but nonetheless it's half a meter. And then the flow areas, again, same table D.2, and then you can get information from that for the area of the inner tube. Now, if you want to find the area of the outer tube, space between the outer tube and the inner tube, the annulus basically, again, you have to do the difference, and then based on that, you use calculation. Okay, so it's basically the difference in the area. The difference in the area of the whole outer tube minus the area of the inner tube. And then, obviously, if you find the tubing sizes, then you can find the velocities, because we already know the properties of the flow rate. Like we know our mass flow rate of both fluids. We know also the density of the fluids for both of the fluids. So then, when you apply the areas, then you can find the velocities for both of those. Okay. And then, obviously, VC means the cold. W means warm, right, or hot fluid. However you define it. And also, we can also find the mass velocity of those fluids as well. All right, and now it gets more involved, right? Because now we're actually looking at other properties or other information that we need to do our calculation. So, for example, we have the annulus equivalent diameter, right? And why are we doing that for the annulus, not for the inner tube? The annulus, remember, is a tube within a tube. So, why do we have to find the equivalent diameter for that?
It's missing the middle.
Yeah, so it's a non-circular. It's a non-circular tube. That's why we're doing that. And the equivalent diameter is going to be used for what? Which number?
What was the question?
Which number is going to be used for?
Right.
The equivalent
The
diameter.
Reynolds number?
Nusselt's number. Good. So Nusselt's number used for. And also, you can also find the hydraulic diameter, and the hydraulic diameter is actually going to be used for what? Hydraulic diameter is used for what? There you go. So make sure you differentiate between those two. And those are the two that were found out here. Obviously, this wasn't labeled in here, but nonetheless, this should be also included because you need to use that later on. Okay. But our initial calculation is going to involve the equivalent diameter. And then, so as a result, the Reynolds number that we find out, right? So there's going to be two types of Reynolds numbers you're going to use, right? One is going to be used for the Nusselt's number, and the other one is going to be used for the friction factor. So in this case, we're actually looking at, because based on the methodology given to you in your book, we're first going to go through the Reynolds number for the Nusselt's number, and then Nusselt's number will give you what? What can the Nusselt's number give you? The Nusselt's number gives you what coefficient?
Convection.
Convection coefficient, exactly. Or any heat transfer coefficient. that we need here. So that's where you find the Reynolds number for both the cold and the warm fluid, and the Nusselt's number based on that is going to be, for this case, I believe we have I think we end up with a turbulent flow. I don't remember the exact answer or the solution for this, but I think we end up with a turbulent flow. But nonetheless, I would encourage all of you to have or practice your if statement, right? If and else statements. In this case, you'll have two if statements. We have one for the case where the Reynolds number is greater than 10,000, and the other case where the Reynolds number is greater than is greater than 10,000. Okay, so the reason we have two of these 10,000s here is because one is for the warm fluid, one is for the cold fluid. So you actually end up with four if statements. Four if statements. I'm going to write that down. Four if statements.
Laminar and turbulent for cold, laminar and turbulent for warm.
Perfect, yes. So laminar, cold, warm fluid, and turbulent. So basically these are the four that you end up with. Turbulent, cold, and warm. Right. And obviously these equations will be the exact same. Right? The only difference is for different fluids. Same here. These equations will be the exact same for the turbulent. And that's all this code means. And I think I've provided a template of it so you can also look that up as well on Blackboard. But anyway, this is to give you an idea. It obviously looks a lot of lines, it's quite a bit involved, but when you get the hang of it, right, when you compare it with what the methodology in your book versus what you're reading through from the slide or from the MATLAB code, it's basically the exact same thing. And then based on the Nusselt's number, and as was mentioned, you can find the convection coefficients. Okay? And you find the convection coefficients, the three convection coefficients. In this case, you only end up using two of them because the inner tube or the inner coefficient is actually a function of the H sub I. Right? And so one of the solutions that we wanted to find, what is the overall heat exchanger coefficient? Right? So in this case, it's going to be 1 over HP plus 1 over HA. The HA is the annulus convection coefficient, and the HP is the tubing, the inner tubing coefficient. Okay, and then so you have one solution. So we've taken down one. We're done with that. But also actually in a way we actually kind of also have to find the temperature, outlet temperature as well. So because we have found this overall exchanger coefficient, we can actually double check to see my estimation of the 10 degrees if it's close or off. Okay. For the water. So the water exit. Remember, we've given the inlet and outlet conditions for the refrigerant. Right? We're also given the inlet condition for the water, but we're not given the outlet condition for the water. And that's what we can double check to see if that's correct or not. And so what you can do is go back to this table. I mean, go back to the table in the book and then write down the equations for those. You find the capacitance, which is basically your mass flow rate times your heat capacity for each fluid. And then you can do the ratio of capacitance, which then you can use to apply to find your effectiveness. And before you find your effectiveness, you need to find your surface area. Right? So it's the surface area between what? The surface area between what?
Between two pipes.
Exactly. Exactly. Surface area between two pipes. Basically, where the heat transfer is going to occur through the fluid that's inside the pipe and the fluid outside. Okay. So the effectiveness, that equation is given to you. In this case, we're going to assume it's a counterflow, right? And in terms of the efficient system, which one's more efficient? Counter? Yeah. So that's why we're assuming it's a counterflow, right? Because we want to get the most efficient system. Okay. And based on what's given to you in your book, you can then find the equation and apply it, and you will get the temperature. And I believe when I did the calculations on my own, I found it to be, I was off. I think I was off by quite a bit. I think it ended up being close to 17 or 16 degrees Celsius. So it was a very small temperature difference. Mainly because if you notice, what was the flow rate of it again for the water? And let's see. Another 4.5. It was like 48.5 kilograms per second. Mm-hmm. And then for the refrigerant, I think the flow was 0.1 kilogram. So as you can tell, there's a huge difference in the flow rate. So even if the refrigerant has a high capacity, let's say it has a high capacity, heat capacity, because of the flow rate, the capacity goes down. compared to the water. I think that's a big difference. So as all the temperature in the water, or the energy that's basically transferred to the water, it's not as significant. So as a result, it is significant, but it doesn't affect the temperature as much because of the large capacity it has, overall capacity that it has, because of the large amount of fluid going through. Okay? This is something to keep in mind when you do analysis. And obviously, as you notice, I crossed out the small t2, which means it's the outlet conditions or outlet temperature for the refrigerant. Why do you think I crossed it out? Why did we calculate it for?
It's given.
Exactly, it's given, so you don't have to worry about it. And obviously, you don't want to change it, because if you change it, then it will change all results as well. But then we'll have to also account for, actually, let me go back quickly. Something very important, obviously, because you guys mentioned that obviously it doesn't change, right? This temperature doesn't change. And because of this constant temperature, saturated condition, we only account, if you notice here, the capacitance only accounts for the heat of vaporization. It doesn't account for the temperature difference. First of all, because even if you account for the 0.1 degrees, it's a very small amount. And more importantly, it's only going from vapor to liquid. Okay? That's from liquid to, is it vapor to liquid or liquid to vapor? The problem.
Liquid to vapor.
Liquid to vapor. So if it's going from liquid to vapor, then all you account for is the heat of vaporization, pH. And that's where this comes in handy. The enthalpy of vaporization is where you apply this value. Okay. And obviously we don't need it for this because there's no phase change for the water. All right, and then from there you can also do the log mean temperature difference. So in this case, the T2, again, T2, T1 is going to be, T2 is going to be 5.1 and T1 is going to be 5, just so you can avoid the potential negatives, right, or zeros, right? And as a result, you will get a log mean temperature difference based on that. And then using this log mean temperature difference, you can then apply it to find the overall or total heat transfer rate, right? Which will just be the overall heat exchanger coefficient we found, the area, the surface area, and the log mean temperature difference. Okay? And we assume in this entire problem there's no fouling at all. So that's why if you notice the capital F does not exist here, or it's equal to 1 basically. Actually, I messed up. It's 1. And also, at the same time, we can also find the heat transfer rate for the hot fluid and the cold fluid. If you notice, the heat balance is going to be the capacitance times the capacitance of the water, right, times the temperature difference of it. So in this case, it's going to be 18 minus whatever the optimal temperature was, or is. And then the heat transfer of the cold fluid, if you notice, I only put the capacitance as it is, no temperature difference. Why? It's repetitive, but why is it again? So I'll only put the capacitance. I do not include the temperature difference.
It'd be 0 if you put the temperature difference.
Exactly, it would be 0, right? Or even if it's 0.1, it's going to significantly reduce or significantly change the value. So in this case, we actually don't account for that. Because again, most of the energy is coming from the vapor. Basically the phase change, liquid to vapor. All right, and then the last part, the heat transfer area and loose tube length, we don't have to find that because guess what? We already have the information for the entire heat exchange, so you don't need that information. So you can live with that. All right. All right, so now we already saw everything about heat balance. Now let's go back to the mechanical balance, you could say, okay? The mechanical energy balance. In this case, it's the friction factors that you get involved in, right? The flow through the pipe, the pressure drop, that's where the mechanical energy balance comes into play. So we talked about heat balance, now let's talk about the mechanical energy balance. And in this case, we have to talk about friction, which then obviously involves viscosity, which you'll see that in, obviously, when you apply Reynolds number. So again, you guys have to find the roughness factor, so you know it's copper, right? So then look it up in your book. I think it's from chapter 3. You can look it up, and you can find both for the pipe, or the tubing and the annulus. Again, both are the same because they're both copper. And then we have a hydraulic diameter and pipe diameter over here, which again, this is to find the friction factor. So make sure you use hydraulic diameter, not the equivalent diameter. And I decided to use a Swami-Jain equation, but you can use whatever equation you want. There's Chain equation, Allen equation, Churchill equation. It's up to you, whichever you want. I have no issues with it. Right? I have no problem with it. As long as you use something that's authentic, and reliable. Right? So don't go look at someone else or come up with your own equation and use it. That's not going to work. But go ahead and apply that. Okay. And so basically, if you notice that the F sub A or F underscore F sub A or F underscore A, and also the F underscore P, those are for different Reynolds number as well. Right? So again, just like we did for the Nusselt's number case, right? Here we do the same thing as well. So how many segments do you think we'll have again? We have turbulent, laminar, we have cold fluid, hot fluid.
4.
Yeah, we'll have 4 again. Exactly. We'll have the same scenario again. But this is the difference is that we're looking for friction factor, not Nusselt's number. So yeah, that's pretty much it. And you can get these equations on your own, and you can plug and chug and see for yourself what happens. And after you find the friction factors, and I think for these, they end up being, I think, laminar flows, I believe, because they're tubing, the small pipes, for the most part. But nonetheless, from using that information, then you can apply and find out the pressure drop. And the pressure drop, you guys know the equation, you guys are already familiar with it, right? The whole FLD, right? FL over D V squared over 2G. Right, you guys seen it several times, right? So you just use the same concept over here as well. There is a small difference for the annulus one, or basically the non-circular one. Just like make sure you account for that. And then I divide by 1,000 here because I want it to be in terms of kilopascals. Okay. Any questions? Yes, I will post these slides. Absolutely. We still have to do our own work. All right. All right. So just to summarize what we just went over, basically I just showed you how to do the double head exchanger, and also previously I showed you how to do shuttle tube and crossflow heat exchangers. And mainly I showed you how to do it in MATLAB, but you can also do it by hand, and also you can do it by Excel, and any other software that's available at Biology to do that. Okay? So you're not limited by MATLAB only. You can use whatever software. The reason I like MATLAB mainly because I'm used to it, and it works better for me, especially if you're trying to plot data and you're trying to show data. You can actually program it, and all you have to do is just program it once, and that's it. You don't have to worry about it again. Especially if you're going to display information, make tables, make figures. Okay. Any questions? All right, we're done. And then we will have the closed door PDR sessions. Or